Hey everyone, welcome to part two of the radio control hypercar project. As I talked about in part one, I really want to push the boundaries of what is possible for an RC car, particularly with aerodynamics. When we're talking about generating a lot of downforce, this is going to require a unique suspension that can handle those loads, which is the exact kind of suspension that you would find on a Formula One car or any other prototype style race car. Obviously, this is a completely experimental suspension design for an RC car. I don't think anything like this has been attempted in something as small as a 1/10 scale RC car. I'm purposely not going to focus on the basics of suspension design, as I think this video is going to already be quite long, and there's some amazing YouTube videos already out there on the subject. I think I will put in some links down below so that you can check out some of those. I really want to focus on the aspects of the suspension design that are unique from your typical road car or radio controlled car suspension. Now let's start with the front suspension. I've printed out at least 20 or more iterations of the front suspension, and I've even remade this video like 4 times now. Needless to say, this entire suspension is a work in progress, but I think it's really important that people know how iterative the design process actually is, particularly with a highly integrated car like this and a designer that doesn't necessarily know what he's doing. The design isn't perfect, but the most important goal right now is to get the car up and running so I can find out all the other issues that I don't know about yet. The front suspension is a typical unequal length double wishbone suspension found in most performance-oriented cars today. To design this, I created a few sketches of the front suspension from the front, side, and top perspectives. These sketches lay out the actual kinematics of the entire suspension. Starting with the front view, we have the upper and lower control arms here, and these are actually controlled parametrically, meaning I can easily make changes to the geometry and the entire kinematics of the suspension will change automatically for me. I didn't mention earlier, but the suspension is being designed around 8 to 9 millimeters of roll compression and 3 to 4 millimeters of heave or pitch compression and 5 millimeters of extension or droop travel with a ground clearance of 10 millimeters. I'll talk more about these numbers later, but the reason I bring this up is because these numbers are absolutely huge for a full-size race car. Something like a Formula One car only has 30 millimeters of total ground clearance, which is like 3 millimeters at 1/10 scale. But to make up for the relative surface roughness of your typical pavement, an RC car really has to be set up more like a rally car than a track car, unfortunately. Here on the right, I actually have the steering spindle axis with our static camber of about 2.5 degrees, and there's around 2 degrees of camber gain throughout the suspension travel range. I have some kingpin inclination here as well to try to help mellow out the caster rise so that I can make tighter clearances on the body. I have no idea if these values are actually going to end up being good for the car. I need to actually do some testing and see how the tires actually perform. Up above here, I actually have the steering arm axis. These lines actually are extended out so that I can see how they tie all the way back to my virtual swing arm or roll centers. And I also have my pull rod geometry shown here. I chose to go with a pull rod suspension over a push rod suspension for a couple of reasons. First, a pull rod design puts the rocker arms lower in the chassis and allows them to be mounted to part of the monocoque that was already heavily reinforced. I'm actually having a rib running down the bottom of the monocoque. Because of packaging and the subsequent pull rod angles, there's actually a lot of force going through the pull rod, and 3D printed parts are much stronger in tension. A plastic push rod would have needed to be much stronger, and rather than like 4 millimeters square, it would need to be something like 6 to 7 millimeters in dimensions. Most of this is a pretty typical double wishbone geometry type stuff, but with high downforce, I need the car to be as stable a platform as possible. Small changes in ride height can change the amount of downforce and the front to rear balance of that downforce. So we really need to deal with what I call the evil antis. And the antis are anti-geometry. So this here is a side view of the suspension where I've laid out all of the anti-dive geometry. Honestly, I didn't know that much about anti-geometry before this project, so I'll do my best to try to explain it all. And this is going to be a simplification, but a car actually rotates and pitches and rolls about its center of gravity when it brakes or turns or accelerates. As you can see right here, this is my estimated center of gravity for the car. So if the car pitches about the center of gravity, we can actually design the front suspension angles to resist part of that pitching motion and try to transfer it into a different motion. Anti-dive is typically expressed as a percent, where 100% is where the car will not pitch at all about its center of gravity, and 0% means there's no kinematic resistance at all in the suspension to pitch. As you can see, this particular car is set up with around 50% anti-dive, which is probably too much, but the car has a really low center of gravity. This is a tricky subject as there's no hard and fast rules around how much anti-dive to use, but anti-dive does have some consequences that we'll have to check out as we're testing it. First, obviously, anti-dive reduces suspension compliance and can hurt low-speed handling. Secondly, the control arms are actually pointed towards each other, and depending on the control arm width and the distance between the upper and lower control arms, it can become impossible to package high amounts of anti-dive. And lastly, anti-dive really messes with something called bump steer. And bump steer is the tendency for the steering angle to change as the suspension goes up and down. Once you have anti-geometry, you have to evaluate your steering arm axis in 3D CAD software because there's no longer a ideal position for the steering arm axis where there's going to be no bump steer. The best you can hope for is to place the steering axis in a place that minimizes the bump steer within that suspension's travel range. This design results in right around half a degree of toe out under full compression and a little less than a half a degree of toe in under full extension. It's not ideal, but I'm going to test it out and see how it dries. It's very hard to optimize this kind of geometry in a small scale. Now, before we actually talk about the rocker arms, let's go ahead and look at the suspension in 3D. We have the upper and lower control arms here, and the pull rod is obviously connected to the upper control arm and comes down to the rocker. The steering knuckle is a very typical ball type knuckle. I'm not sure this design is going to stay, but I wanted a knuckle design that would allow for the mounting of front motors in the future. The steering angle is fairly limited to around 25 degrees, which I think is actually fine for this type of high speed, high downforce car. I've designed a steering knuckle with more angle, but it's going to foul with the body and it's going to be very hard to package. I have a tie rod here that's connected to a custom designed servo horn. I'm not super happy with this design, but I need to drive the car and actually see how it performs. When I get into the actual monocoque design, you'll see there's very little room for packaging of the steering in this car. I wanted to try a little bit of innovation with the control arms themselves. So rather than using metal ball joints like most RC cars utilize, I decided to test out a flexure joint. A flexure is just what you think it is. It's a neck down portion of the control arm where the arm will actually pivot from. So why did I do this? Well, there's three main reasons. First, this eliminates some ball joints on the car, which can save some weight. Also, because we have no ball joints on the ends of the control arms, the cutouts in the monocoque for the control arms can be much smaller, and that allows for better aerodynamics and airflow, particularly around the nose of the car. And lastly, flexures, unlike a ball joint, have no friction since they're just bending the plastic itself. Now, I'm sure someone will notice flexure does make a suspension stiffer. So it does add spring rate to the car, which just means we need to run a slightly less stiff coil spring, which is no issue at all because I think that the coil springs I have for this car are not going to be stiff enough anyways. Next, I know everyone is worried that the control arm is going to break at the flexure. And what I have to say is that this is just an experiment and things failing is how we're going to learn. I've done some limited testing and the first control arms broke quite quickly. And this was because of how the 3D printed slicing software was working. It actually made squiggly lines to fill in the flexure joint, which ended up making them very weak. So I learned to print them with enough walls that the narrow legs of the control arms were essentially solid. And this causes the plastic to be deposited lengthwise over the flexure, and which is in the direction that the actual forces are going through the control arm. I've tested Pt2 and PLA Plus for the control arms, and I found PLA Plus to be by far the strongest filament, and I think it'll be more than sufficient for initial testing. I can't break the control arms by hand. I can overflex them past where their max deflection angle will be, and eventually they will crack and break, particularly with Pt2. I'm not too worried about this as the actual control arms only flex about 8 degrees total between compression and extension. Later versions of the control arms will be printed in either carbon fiber polycarbonate or carbon fiber nylon, depending on which proves to be stronger. And both of these materials are much more impact resistant. Let's talk about these rockers and pull rods. The suspension design is completely governed by aerodynamics and the ability to package overly large radio control car size components into this small little package. I can't remember, but hopefully I mentioned earlier that the pull rods are at a rather shallow angle to the control arm. This isn't ideal because there are a lot of forces being transferred at less than ideal angles that will cause bending stress in the arms and a lot of friction in the actual mechanism itself. So I have embedded some tiny MR63 bearings inside the rockers themselves, and I have this extra brace that ties the two rockers together to prevent bending at the monocoque mounting points. The other disadvantage of this shallow angle between the pull rod and the control arms is the actual motion ratio of the suspension isn't great, which I'll go into more detail here in a second. I played with a lot of different designs for springs, from torsion springs to extension springs and custom damper bodies. But ultimately, for this version 1 prototype, I just decided to give myself some room and route the shock shafts outside the monocoque. It's not going to affect the aerodynamics significantly, and I can easily change this later, and I can just use off-the-shelf radio control shocks and springs so that I don't have to try to develop those myself right now. Now, this is where I messed up my rocker arm design a couple of times. Rocker arms actually change how a suspension responds in a couple of key ways. First, rocker arms actually can change the suspension movement ratio. So before I dive into this, we just need to talk a little bit about suspension movement ratio. All the different components in the suspension can actually affect what they call the wheel ratio. And this is the ratio between the movement of the wheel and the movement at the spring and the damper. So for example, this car, the wheel can travel 9 millimeters when it's in bump, but the shock and the spring will only compress for 4 millimeters. As I alluded to earlier, the shallow pull rod angle results in a less than ideal wheel ratio. But we can also change that movement ratio in the rocker arm itself by changing the ratio between the input lever arm length and the output lever arm length. This has advantages and disadvantages. In full-size cars, this allows for really tiny dampers and springs like what you might see in Formula One, which allows for lighter weight components and better aerodynamics. But it also multiplies the friction ahead of the rocker arms, and the springs and dampers must be correspondingly stiffer. So because radio control car dampers are very simplistic and have no real high-speed valving, they are not very effective over short travel ranges. Just not enough oil is being moved through the piston. So I've designed the rockers to have as high of a ratio as possible between the input and the output, meaning I want to increase the movement at the spring and damper as much as possible within the packaging constraints of the monocoque. Now we run into the other effect of the rocker arm suspension, and that's that they do not transfer force in a linear manner, meaning that the motion of the rocker relative to the pull rod and the shock shaft actually changes the movement ratio as the suspension is going through its travel range. This is actually a great feature for race cars with rocker arm suspensions because they can actually create a rising spring rate or a progressive spring rate, meaning suspension becomes stiffer as it's compressed. So you can run a softer spring to gain traction at low speeds, but you don't bottom out when you go over large bumps. I'll flash up the formula for all of this. What I want to talk about is how this suspension actually works at scale. I got everything designed and I printed out a nice sample suspension and noticed some strange behavior with the suspension rate. As the suspension initially would get stiffer and then actually become softer as it got near the full compression. And this is the difficulty of packaging a tight race car suspension geometry into an RC car. Things like the ball joints, which are just 5 millimeters in diameter, would have to be 50 millimeters or 2 inches in a full-size car, and that's just gigantic. So I went through a lot of iterations in CAD of the front control arms and rockers, and I tried to make the suspension have a rising ratio through at least the majority of its travel range. I think it's about 90% of the travel range is a rising ratio. This is just another reason at some point it'd be really nice to have an active suspension in the RC car so that we can kind of take this into effect. So I'm still not done talking about these rocker arms. We need to talk about Heave springs. So I mentioned in the beginning that we needed a suspension design that can handle downforce without actually bottoming out the car. Most cars today have 4 coil springs, 1 in each corner. If you have a lot of downforce, The easiest way to actually fix this issue of bottoming out the car from that downforce is to run a really stiff spring on each of these wheels. But this can cause the car to be overly stiff and handle erratically. So enter something called the Heave spring. And the Heave spring is a spring that is only engaged when both wheels are compressed at the same time, and typically only after a certain amount of travel. This allows the car to have a much softer roll spring for each wheel that gives the car better low speed handling and grip. There's a number of ways of implementing a heave control in a suspension, but I've chosen the easiest to package route, and that's a 3D printed TPU or flexible urethane band that is tied between both rockers. TPU isn't the perfect material, but it's easy to 3D print, and so I can tune the different thicknesses, and it is somewhat self-dampening. So as you can see here, I've actually designed the springs with some holes, allowing the spring to easily be compressed. The spring is actually designed to be a bit longer than it needs to be so that it's not actually engaged until 3 millimeters of heave compression occurs. This means at low speeds, only the roll springs are acting on the suspension, but as the downforce increases, the heave springs will start to come into play and actually stop the ride height from being lowered past 3 millimeters. I know this is confusing in CAD, but remember it's a pull rod suspension, so all the forces are actually backwards, and the rockers are actually moving apart from each other as the suspension is being compressed.
Okay, so it's a little easier to see. You can actually see this is the brace between the two sides of the rocker arm. This is where the steering tie rod will come in. Again, this is just a mock-up. Those are your two roll springs, which will actually come through here. There'll be two arms that go to the shock shafts, and we'll have some coilover shocks further back inside the chassis. And then you've got your heave spring right here. So the cool part about a heave spring is that, as you can see, we can roll relatively easily. There's a slight amount of transfer back to this, and you can take care of that with an anti-roll bar, but it's actually not that significant because the mode that we're trying to handle here is actually being able to let the car roll over bumps with a relatively light suspension. But when both wheels try to compress, you'll see that the heave spring in the middle will have to go into tension, and you'll just have to take my word for it, but the spring rate more than doubles. It's actually quite stiff when the heave spring comes in versus this is very light.
Okay, so let's take a look at the rear suspension. It should look very familiar. Basically the same setup as the front with some different angles. We have roughly 1 degree of camber, about 0.5 degrees of toe in for stability. Since there's no steering, I was able to actually route the shock shaft over the top of the control arms and the rockers, and I have some L brackets that will allow the shocks to actually be mounted to a bulkhead that ties together the two halves of the monocoque. So the coolest feature of the rear suspension is that it's actually a cantilevered setup, just like in a Formula One car rear suspension. This means that the lower control arm, which is typically below the axle axis to allow for a drive shaft or the axle itself, is actually going to be in line with the axle. Obviously, with a hub motor, I don't need to package a drive shaft and go to the extent a Formula One team does to have the drive shaft actually run through the lower control arm. So why is this design so important? Well, it's because of aerodynamics and the diffuser. With a conventional control arm geometry, when you're designing the rear diffuser, you only have a couple of packaging choices. First, you can design a diffuser that stays entirely below the rear lower control arms. This is typically what you would see in a sports car or even a radio control car that might have a diffuser. I'll go into depth in my aerodynamic design videos, but having that limited space below the control arms restricts how much downforce the diffuser can make and also causes the balance of that downforce to be placed further rearward. The second option is to put the lower control arm right through the diffuser. This causes a few issues. In a full-size car, this greatly decreases the efficiency of the diffuser because you have all of these components messing with the very sensitive airflow under the diffuser. This is even worse in a radio control car where the control arm is much thicker, relatively speaking, and the pull rod is also thicker, and that's going to interrupt all of the flow. In fact, when I did the CFD of this configuration in an RC car, it actually had less downforce when I ran the control arm through the diffuser than just having a smaller diffuser that actually was below the control arms. The cantilever design also does add one more change to the suspension dynamics, and that's the last anti we'll be talking about, and that's anti-roll geometry. So just like anti-dive and anti-squat, you can design a suspension with different geometry to actually resist roll. And in this case, it just happens that there's a force acting on the bottom of the tire trying to push it in on the outside wheel in a turn. And that's going to cause a torque moment about the pivot at the control arm, which is going to try to pull out the upper control arm and raise the suspension, which causes an anti-roll type action. I think this is good for a rear weight biased car, and we'll just see how it performs during testing. There's a little bit of anti-roll in the front suspension as well, just coincidentally due to how I designed it, and we'll see how that works out once we get it going. I also have these extra members here on the lower control arm that are essentially tie rods. I copied this from a Formula One suspension design, and I kind of like it. There's a flexure on the tie rod, which is actually integrated into the control arm itself. The tie rod only moves about a degree throughout the entire suspension travel. But what's cool about this tie rod setup is that as the car rolls and compresses and the outside wheel suspension is compressed, there's a small amount of steering angle added to the rear wheel, which helps to stabilize the car in high speeds, which is very similar to what is used in Formula One car suspensions as well to stabilize the car. So I know this is a long video, but that's the suspension design for the RC Hypercar in a nutshell. Let me know in the comments down below if you guys have more questions or want me to expound on different details of all this. I'm planning on skipping kind of the design around the monocoque and all the mounting points unless you guys are really interested in seeing how a monocoque is designed and how all of that's laid out. Again, it's just going to be a lot more CAD and a lot less action and things actually happening. So I'm hesitant to do that and not just skip forward to the aerodynamic aspects of this build. That wraps it up for this video. Stay safe out there.